Hello everyone, welcome back to this material characterization course organized by NPTEL, and we have been looking at the tutorial class for solving some of the optical microscopy and calculating some of the microstructural parameters like such as grain size, volume fraction, etc. In the last class I just demonstrated some of the standard statistical methods how to represent the microstructural data, for example, volume fraction and so on. I will continue the same exercise in calculating the volume fraction using the micrographs. In the last class what we have done, we have just demonstrated how to use a graticule in an eyepiece on a microscope itself and look at the various fields and then take the data or random sampling from the microscope itself, but using a micrograph how to do the same analysis, that I will just show you. Look at the slides what I have shown here. This is the same microstructure. Instead of graticule we are now putting a grid points of our choice. For example, if you see that here also the method is called point counting, but then depending upon the size of the micrograph, then you can use the traverse line. In this particular case study 9 traverse line were used like this, what I have shown here. So, the general rule is the distance between the traverse line should be good enough, and the golden rule is no two grid points fall on the same region of the interest. For example, here in a black face no two adjacent points from all the sides should fall in this point or this region. So, that is the golden rule. So, if you look at this point, you can see that so none of this intersection, the grid points falling on the second face, that is why it is 0. And here you see that, you can see that point number 1, point number 2, and this is taken as half. So, it is 2 and half. So, similarly it is 1 and then 2, rest all the grid points are not falling on the second face. So, here if you see, this is only taken as half, rest all the grid points are not falling on the second face. So, this is half. So, like that the data which I am going to present on the blackboard is 9 traverses and each of 46 points on a larger area of microstructure, but it is just only a sample is shown here how the counting is done and so on. So, I will just put the data on the blackboard, and remember we are now interested in, instead of using a graticule on a microscope, and we are using a micrograph to calculate the same parameter volume fraction, you just see whether we are getting the similar values. So, I will write the results here. So, as I mentioned, 9 traverse lines were used on a micrograph, each of 46 points on a larger area. So, we have seen this, the point fraction can be calculated either by the number of perlite area divided by the total, that is 9 times the 46 points, that is sigma n, which is also equivalent to the point fraction divided by the 9 traverse lines. So, that will give you the PP like we have seen in the previous example. Now, we will just put the tabulation. The 9 traverses were used to obtain this data. So, this is the traverse number, column 1, column 2, number of points in the perlite P perlite, column 3 is a point fraction, that is PPI. So, column 2 is the raw data, that is we actually count from the micrograph. Column 3 is obtained divided by column 2 by 46. So, you get this sigma p and then sigma ppi. So, you substitute that here. So, what you will get is around so you can calculate the standard deviation, which is 0.2355, and then standard error of p is nothing but is 0.00785. So, what I have written here is we have simply substituted those values into this formula, and then we get the P p bar is equal to 0.1763. Standard deviation is this, standard error is this, and for 9 measurements, that means n minus 1 is the degrees of freedom, 8 degrees of freedom. The value of T 95.8, that is T 95 n minus 1 is 2.306. From the table what we have just did in the last class, you can find out this, leading to a 95% confidence limits of plus or minus 0.0181. So, now we can present the data in this fashion. What I will do is, so what we are getting from this using the traverse line, and we are getting the value of 0.18 plus or minus 0.02, which is very close agreement with what we have calculated using the example what we have seen in the case study of using graticule and a microscope. The value appears to be very close to this value. So, the same thing can be demonstrated using the linear analysis of the similar microstructure. What you can just have a look at the other slide, what I am shown here. You can also look at the point fraction. You can use the linear analysis to calculate the colony size or a grain size of the ferrite phase or the colony size, that means the perlite phase, and you can have the micrograph like this and then take the traverse line like this. And here please understand, we are interested in measuring the linear intercept, that is L. Okay. So, what I am going to demonstrate here is, look at this traverse line. It could be n number of traverse line, using that the golden rule or statistical rule. Make sure these traverse lines are far apart and no two intersection will fall on the same thing, something like that. So, what I have shown here is this is this is where the intercepts are calculated like that. I will just show you how this is obtained. So, for example, if I start counting from this line, for example, this area what you are seeing here, if I can just draw a edge line like this, vertical line, that is what is shown here, for example, this one edge, and then if I the other intersection, if I draw another vertical line, it is shown here, the next line. So, now I will make sure that I am using a transparent sheet on this and then making this vertical mark on this micrograph, assume that, and the moment I make this two vertical line on these two intersections, first one here and second one here, then I will move the tracing sheet to this. Now, the second line what I have drawn here is become the first line for this intersection, then I will draw another vertical line because this is another intersection. So, like that I will keep on moving this transparent sheet and get a full set of a transverse, then I call it as 1. So, like that I will keep on doing this for n number of measurements, and then for each traverse I will simply measure the length in terms of millimeter or centimeter and so on, any unit, and then number of intercepts involved. For example, here for example 1, 2, 3, 4 and 5. So, 5, that is Ni is involved. Here it is 10, here it is 3, 1, 2 and then 3, 1, 2, 3. So, these two are very close. So, do not get confused. So, like that you calculate the intercept and then try to measure this linear analysis using the intercept method. So, now I will just tabulate the values on the blackboard for the reference. So, what I am going to just tabulate the data. See, I just written here 18 traverses, each on 260 long on a larger micrograph obtained at 500x magnification. See, this magnification you have to decide whether the microstructure which you are looking at is representative enough to calculate these values. You can always do it at 200x or 100x, which may be very meaningful, but if your microstructure is too fine, then you may have to choose to appropriate magnification. And then, as I said, you cannot rely on just calculation on each, only single micrograph. You have to maximize the number of micrographs to obtain a meaningful result. So, you can also say that instead of 18 traverses 260 long, you can say 9 traverses about 520 long. So, for the convenience you can tabulate it in any form, because the number of intercepts you are going to count the same. So, that is why I have said that the length fraction of this particular case LL is simply obtained by dividing the length whatever we are going to tabulate by 520. So, you can use 18 to 60 or 9 520, both of them are going to give you the same result. So, let me just if you look at the complete data using the 9 traverse line and the length of the perlite L perlite in mm was calculated like I just showed you on the slide, looking at each intercept value, and this is the number of such colonies, and that is Ni, and then the length fraction is LLI. So, the column 2 and 3 are raw data, column 4 is obtained as column 2 divided by 520 like I just written here. So, if you can just substitute these values, we are interested in obtaining LLI, that is average length fraction, is summation of so what we have got there 1.1648, this summation over LLI divided by 9 is this, and then we can calculate the S, which is nothing but 0.0323, and then standard error so this is small s and this is a capital S, just to differentiate the error and the standard deviation. So, the degrees of freedom is 8. So, same thing, you use the same value T95 8 is 2.306, which lead to the confidence limit of so you say that T95 8 which gives the 95% confidence level limit, which gives to plus or minus 0.0248. Now, we can present the result LL bar 0.183 plus or minus 0.025, which may be rounded off to 0.18 plus or minus 0.02. So, which is again the VV what we have obtained in the previous calculation lies in the range of so this is the conclusion. Whether you use a point count or whether you use linear analysis, you get the similar result for obtaining VV. So, what I have just demonstrated through this case studies is that you may use computer for calculating many of them, or you may be using some of the software readily available in your laboratory. It will just clicking the mouse button, you will get all these values, but you should know how these things are, what that software does, maybe involving some kind of a statistical analysis like this, which you should actually try to see with your some readily available micrographs with you. then you will appreciate the result much more better rather than simply taking this from the software. So, a similar analysis can be done on grain size and colony size, which I have not shown here, though I just started doing on the slide, but in another class I will just demonstrate some of these grain size calculation. But for this the case studies, what we have just looked at is by using microscope itself, using a graticule, or you can use the micrograph itself to calculate the volume fraction using this simple calculation. But the point which I am trying to make is the analysis are very elementary, but the data presentation is very important. That is why we introduced some of the statistical methods which you should know, and then how to present the result. You should not just give one value, you should have the error bar and you should have standard deviation and confidence level and so on. That is why I introduced some of the statistical methods, and also you should make sure that these sampling is random, and then you should maximize the number of measurements, then your values will be close to the reality or the representative of the microstructure which you are interested in. So, I hope these exercise in the tutorials shown are useful to you. I will give you some of the assignments for you to practice, or you can just I will just upload some of the microstructure like this or some of the particles distribution. You try to do similar kind of an exercise and then get back to me whether it is, if you have any difficulty. Thank you.